Alright, let's start off this video with the challenge problem from the last video. So from the AP Physics 1 equation sheet, you should be able to find the equation the period equals 2 pi over angular velocity. And then from this equation, you can see that angular velocity equals linear velocity divided by the radius. So you can substitute that in to get that period equals 2 pi divided by v, and then divided by r, but then you can multiply the numerator and the denominator by r to get 2 pi r over v, which we know period is also 1 over frequency. So cross multiply to see that v, linear velocity, equals 2 pi times the radius times the frequency, and that matches the equation we are trying to solve for. This video is just going to be free response questions revolving around circular motion. So for this one, we have a ball of mass m attached to a string of length L traveling in a vertical circle, and at the top of the path, the tension in the string is twice the weight of the ball. Alright, and we have a limit to the variables that we can express our answers in. So first, we want to determine the net force acting on the ball at the top of its circular path. Alright, so I see net force, so I'm thinking that we should draw a free body diagram. So there is the center of mass of our ball, and the force in contact would be our tension, and any force not in contact would also be the weight of the ball. Or you could say the force of the earth, or mg. Alright, and we know that tension equals 2 mg. So since tension and weight are acting in the same direction, we're going to call inward positive so we can add those two. So the sum of our forces, and these are centripetal forces, is going to be our weight, mg, plus our tension, 2 mg, so that the net force will be 3 mg at the top of the circular path. Alright, and now we want to determine the speed of the ball at the top of its path. Alright, well, we know force centripetal equals mv squared over r. From part A, we know centripetal force is 3 mg. And our radius is the length of the string L. Mass cancels on both sides, and you can solve for v with some simple algebra to get 3gl square root. And these are the final two parts of this question. So first, we want to determine the time it takes for the ball to reach the ground. So we're going to be looking at our kinematic variables in the y direction. So when the ball is at the top, it has a tangential velocity that is all in the x direction. So that means our initial velocity in the y direction is 0. We know that our change in y is going to be the diameter of the path, which will be 2L, and acceleration is due to gravity, so it's g, and we are looking for the change in time. So we want an equation with no final velocity, so that will be change in y equals initial velocity times time plus 1/2 acceleration times time squared. Initial velocity is 0, and then we can solve for t to get 2 change in y, or rather, I should say 2 change in y divided by acceleration, all of that under the square root. Substitute in our variables to get t equals 4L divided by g, which is the same thing as 2 square root of L over g. and that is part C. For part D, we want to determine the horizontal distance traveled by the ball before it hits the ground. Alright, so we're looking at our horizontal variables, and we can actually use the equation x equals vt, change in horizontal position is horizontal velocity times time. From the previous part, we have v equals square root of 3lg. And then from part C, we have 2 square root of L over G. We can combine what's under the square root because it's all being multiplied. And that gives us 2 times the square root of 3L squared G divided by G. Alright, and then our L squared and the square root cancel. And for part D, we get 2L square root of 3. Here is our next challenge problem. So the first thing we are asked to do is draw and label all the forces acting on a ball moving in a vertical circle at the given points. So at point Y, the only force in contact with the ball is the force of tension. And then the only force not in contact that we have in AP Physics 1 would be the force of gravity, or you could say the force of the earth. And then off to the side, you can do this on the exam if you want, is just to make absolutely sure that they know what forces you are labeling. And in our second diagram, we have position Q. Alright, now we should just think at this point, because it's our second diagram for the same situation, are the types of forces any different? Have any new forces come into play at point Q? And the answer is no, so we have the same forces. They're just in different directions. So we have tension, and we have the force of the earth. Now we are asked to derive an expression for the minimum speed the ball can have at point X without leaving its path. Well, let's just sum the forces on point X, and we're going to call inward positive. So if we sum our forces at X, we're just going to have mg plus t equals ma, but we're in circular motion, so ma is really m times centripetal acceleration, which is mv squared over r. Alright, now we want the minimum speed. That minimum speed is going to occur when tension is 0. So all of the centripetal force is being applied just with gravity. So then we are going to get mg equals mv squared over r. Our m's cancel, and then we can simply say v minimum equals g times r when you multiply both sides of the equation by r and take the square root. So that would be the answer for part B. These are the last two parts of this question. So for part C, we are looking for the maximum tension the string can withstand, which is Tmax, and then we're trying to solve for the maximum speed the ball can have at point Z. Alright, well, remembering our free body diagrams from part A, let's just sum our forces at point Z. again, we're going to be consistent and say the inward is positive. So the sum of our forces at Z is going to be T minus mg, but our tension is a maximum. And that will equal mv squared over r. Right, and then we're just trying to solve for v. So let's multiply both sides of the equation by r over m. Alright. Then we will have r over m times T max minus mg, and then you just take the square root of that whole expression to solve for V max. Alright, and that would be an acceptable answer for part C. Now part D would be more of a handwritten, somewhat lengthy response. Usually 2 or 3 sentences will suffice. They want to know what will happen to the motion of the ball immediately after the string is cut at point Y. Well, at point Y, our tangential speed will be directly upward, and for the sake of time and space, I'm just going to tell you what I think I would write here. Pause this video right now, write out your response, and see if it matches with mine. So at point Y, the tangential velocity of the ball is directly upwards. Therefore, after the string is cut, the ball will continue to move directly upwards until, due to kinematics, it will reach a maximum height and fall back to Earth. At that maximum height, its velocity will be 0. And that concludes this question. This is the final problem for this video. So we have a ball swinging on the end of a string, where point X is the lowest and point Z is the highest points. And on the given diagrams, we want to draw and label possible vectors to represent the velocity and acceleration of the ball at the given points. Alright, so at point X, there's going to be a centripetal acceleration because the ball is in motion. And then any velocity that the ball has is going to be tangential. So there's one correct answer for the acceleration, but there are 2 correct answers for the velocity. So because this is the lowest point, velocity is going to lie on the x-axis, and you could draw it to the right, or you could draw it to the left. Either answer is acceptable as long as the velocity is on the x-axis. So point C is the highest point that the ball reaches, and at that highest point it is going to have a velocity of 0. So right here I'm just going to write velocity is 0. And then because the velocity is 0, and we know that our centripetal acceleration is v squared over r, v is 0, so there's no centripetal acceleration. But the ball still swings back down after it reaches point Z, so there is still an acceleration. But that acceleration is straight down on the y-axis. Alright, in part B, we have a string breaking, and the ball is going to take different paths depending on where it is at that point. So in this diagram here, where the ball is at point X, we know that it has a velocity either to the left or the right on the x-axis. Therefore, for example, it might take a parabolic path that way, or it could also be going to the left. Now at point Z, the ball is at its maximum height. And we know its velocity is 0 and its acceleration is straight downwards. Therefore, if the string were to break at point Z, the ball will simply fall straight downwards. Alright, so that concludes this video and our unit on circular motion. Next, we will be studying gravitation.